All right, folks, let's get going. So the autograder has been run for project 2A/2B. The scores that are on there are not your final scores. In fact, 2A is not even worth the right amount of points. But so the scores, again, they're not final. We're still tweaking the autograder. And there will be a handful of you who put in a ton of effort and then didn't get a lot of points, or even missed a lot of points for some silly reason. So we have a way that we're going to have an effort offset. I'll tell you how that works later. I'll try and make sure you have these scores by Friday if for some reason they affect you for the PNP deadline. So be aware, you can kind of see how your code did on the autograder, but be aware it's noisy. Other, midterm, remember that's on Friday. I'm sure that's on your minds. Hopefully you've enjoyed the breathing room to be ready for that, which is coming. And if you want to know your room assignment, see internet. One last thing, announcements-wise, is one of the TAs really likes this description of A-star and other shortest paths algorithms. So you may find it interesting as well. It's got these nice interactive demos, and it's just an alternate perspective that a TA who's thought about these things many times really enjoyed. So here you can see a fringe and all that. So if you want to play around with that, you might find it useful. All right, any questions before we kick into the day? Yeah. English is not easy. Okay, cool. Okay, so today we're going to be talking, this is a totally new lecture, a pretty interesting one, and I'm going to start by just pointing out we've done quite a lot of stuff. We're now wrapping up the second phase of the course, which was data structures. And if we think about all the things we've done, we had a very beginning, we spent a ton of time on Java, and overall we've gotten much better at programming, hopefully. We've seen Java, IntelliJ, JUnit correctness and timing tests. You guys have designed your own data structures where you've been able to combine things together to make, that is, to combine different data structures together to build other data structures. And you've been able to verify that they work, or at least, hopefully they work. We spent a lot of time on the asymptotic analysis of the runtime and space complexity of our algorithms and our data structures. We've talked about all these different abstract data types, like lists and maps and sets and priority queues and so forth, and lots of different ways to implement them. And we've now spent some time doing algorithms on graphs. So it's a data structure that admits really interesting algorithms. And so the question you should ask yourself now is, why? Why have I done this? Why have I spent, I don't know, however many hours, hundreds of hours at this point, I'm sure, on all this stuff. So why this specific body of knowledge, and why are there people out there that want to hire you? Not necessarily as programmers, but just they want you to have these skills. What do you think? Why this body of knowledge? Sure. Yeah. Way back. All right, that are otherwise intractable. Yeah, so it's nice to be able to write code that is efficient. I agree with that. You can solve problems that are useful. And those problems, I guess, maybe it's more important to note that, let's see, so these, why is it being slow? Okay, yeah. So otherwise intractable. And these problems are real-world problems, like things that actually matter, like you're simulating, I don't know, biological systems or drug dosing or, I don't know, the physics of galaxies evolving. Who knows what else? What are some other thoughts? Why do people care about these specific things? Yeah. It shows an understanding of the language you're using? Got it. Shows an understanding of how computers work. That is, it's a shibboleth, so to speak, of someone who understands computers. I'll let you look up what that word means later. Shibboleth of understanding of computing. All right. That is, if someone knows that you know what a hash table is or how they work, that implies you know what you're talking about. Any other thoughts? Yeah. For fun? Okay, yeah, it's pretty fun, I guess, for many of us. It varies person to person. There's a lot of mathematical richness, like these algorithms problems lately. Yeah. I see. Easier. Oh, for interview. Provides a common platform for interviewing for technical knowledge. That's an interesting thought. So everybody teaches this stuff, so all the companies know that you kind of know it. So then they have this as a basis to work on. And I think this is actually reflective of a more important point, which is that the tools, basically you now have a huge tool set you can use to solve problems, right? I mean, it's all kind of the same as what we saw earlier. So just some reasons you might ask, why are we studying these specific things? I mean, it's partially about tool sets. It's partially about showing off that you know how computers work, how one can build systems, solve real-world problems. And I guess one other thing I want to mention is that I really think we're changing the way you think. Like fundamentally, the way that you're solving problems now is different. I mean, ideally, hopefully at this point, you're starting to break down complicated problems into smaller ones. And since you have all these fancy tools like disjoint sets and whatever else, hopefully you recognize where they can be applied. Okay, so just kind of vaguely. All right. So we're going to refine these skills a bit, and I'm going to try and figure out why my computer's being slow. Let's find out. Is something slow? It's just slow. Oh, okay. Who's at fault? Well, Chrome's using a lot of memory, but nobody's using a lot of CPU. Okay, I don't know. Anyway, well, we're just going to live with it. Okay, so what we're going to do the rest of the day is we're going to solve some pretty challenging kind of A-level problems, mostly on graphs, just to practice and think about how we can solve problems. Okay, so remember we have all these different graph problems. We have path, shortest weighted path, shortest weighted path. Those are A-star, Dijkstra's, and so forth. We also talked about spanning trees. We had Prim's algorithm, Kruskal's algorithm. And so now we're going to start talking about just some other interesting problems. So let's imagine, all right, now finally I've set the stage for our day, somewhat lamely. Let's talk about a new graph problem, which is known as a topological sort. Okay? So the basic idea in a topological sort is we have a directed graph where each vertex corresponds to, let's say, a task, and each edge corresponds to a dependency. So you could think of maybe 0 would be 61A, so you've got to take that before you take 61B or whatever else. So you can think of 0 as 61A, 1 as 61B. And in this case, they are strict dependencies. So unlike 61B, where you can also have taken CS88 or whatever else, E7, here we have just strict dependencies. Okay? And so what you want to do then is try and find an ordering of the vertices where you satisfy all the constraints. So for example, if you do task 7, that's not allowed. Maybe classes is not the best example. Maybe 0 is like, plug in the toaster. 1 is put the bread in the toaster. 4 is start the toaster, right? You got to do it in a certain order. So question for you then is, how would I find, given a graph, a topological sort? So an example of a valid ordering, a valid topological sort would be 0, then 2, then 1, then 3, then 5, then 4, then 7, then 6. If you look at that, you'll see that we're doing tasks in a good order. So I'll give you guys, I don't know, a minute or so to think about where you'd start. It's actually a pretty hard problem, but give it a shot. All right, I also listed some suggestions. Anybody have some thoughts about how you would approach this problem? Anybody I haven't talked to yet? Yeah. Oh, interesting. So start multiple breadth first searches. Multiple breadth first searches from vertices of degree, or we'll call that in degree 0. So the idea there is a vertice of n degree 0 is one that has no input edges. Those are great places to start. Okay, so let's think about this algorithm and see where it gets us. So if we do these simultaneously, I don't know, let's see what this algorithm gives us on this graph. I wonder if this works. Might. So we have 0 and 2. At that point, the next vertices we would collect, I guess, these in common, which would be like 1, 3, 5. Those are all together. Okay, I guess those all come next. Then we have 4, 6, and 7. Does this work? Are there any violations here? Looks good to me, that idea. Interesting. Let's see. I'd never heard that algorithm before. I wonder if it works. Seems to work for this graph. I like that. It's a little ill-defined exactly what you mean by breadth first search from 2 start points, but it's actually not hard to adjust. Yeah. From 3 to 6, for example? From 8 to 6. Okay. Got it. Aha. Good. Okay. Cool. I did not spot that. Okay. So here's a counterexample. I like your algorithm. It's a cool start. And that's, again, how these problems are solved. You start with an algorithm that doesn't work. Whenever you look at people who are doing research, they're not just zeroing in on the correct answer. They're trying something, finding a counterexample. So if you do this, the danger is that 6 will end up, so this new graph, we'd have 0, 2, 8, and then 1, 3, 5, 6. And so things won't work out quite as well. If you're allowing any of the vertices to contribute. Yeah. So in this case, 1, 3, 5, 6. Well, it depends on the ordering. So what could happen is we would have, let's say, 1, 3, 6, 5 or something like that, right? Like the breadth first search might get to 6 first. We can construct a better counterexample, I bet. What's that? 8 to 7. Even better. Thank you. Okay, there we go. Okay, cool. So, All right, so in this newer graph that you've come up with, we would have 1, 3, 5, 7, which isn't so good. Yeah. Okay, but that's cool. I like that. Okay. Yeah. Mm-hmm. Yeah, okay, so start one of these guys, okay? So start at 2, let's say. Go as far as you can get, which is what we call what? What's that algorithm called? DFS, okay? So you do DFS, so that would yield you, for example, 2, 3, 4, 7. And then, I guess, 5 after that. Wait, 2, 3, 4, 7, 5, 6. Yeah, something like that. Okay? So how is that useful? I mean, I think it is, but I'm just curious what you had in mind. 2, 3, 4, 7. Oh, well, if you're just running DFS, though, you'll hit 4. Oh, I see. So you have DFS where it can kind of look back and check its dependencies. So maybe you can build an algorithm like that, but it's more complicated than you really need. This is actually a pretty good start. That if you do run DFS from 2, for example, there is a nice property that we get out of this thing. 2, 3, 4, 7, 5, 6. So what I'll note is that the vertices that come later in this list, you could think about them as the things that you would ideally want to do later, right? I mean, that makes sense. So there is something here. So I'm actually just going to spoil it. I mean, it's hard to get to the algorithm from scratch. I haven't found a good way to do it. So I'm going to spoil it, and we'll see and get an intuition for how this works. Okay, so I'm just pointing out this is a pretty hard problem to solve. We tried a couple approaches. And so the classic approach to this is run a depth-first traversal from every good starting place. So you guys got that basic idea that 0 and 2 are good places to start. And what I'm going to do is I'm actually going to do an entire depth-first search from, say, 2. And then I'm going to do another depth-first search from 0. And I'm not going to clear the marked vertices in between. Okay? And we'll see why. I'm going to show an example, like a demo. And as I do it, I'm going to write down the DFS post order. That is the order in which I return. And I'll talk about the intuition for how this works. And then the topological ordering will be given by the reverse of the post order. Okay? It's simpler than those words made it sound. And so let's check it out. Okay. All right. So let's say we start at vertex 0. Why? Because it has in degree 0. And it could have been 2, but I decided to pick 0 arbitrarily. So the next vertex I'd go to is what? 1. Good. Okay, so we go to 1. Where do we go next? 4. Great. Where do we go next? 7. Okay, we're done with 7. So I'm going to write that down in my post order. Okay. Now I keep going. So we go back to 4 because we're returning. At that point, I'm done with 4. When I go back to 1, will I be done with it? When I go back to 1, I will be done with 1. Yeah. So we have 7, 4, and 1 are our DFS post order. right, when we get to 0, are we done? No, we got to go to 3. Okay, we go to 3, and so 3 ends up in our post order. Now we're not done yet, because we haven't thought about vertices 2, 5, and 6 yet. So what did I say we're going to do? We're going to run another DFS starting from 2, and we're going to leave all of these vertices marked. Okay? So let's start at 2. All right. Oh, actually, sorry. We're done with 0 now. So let's start another DFS from 2. So we start at 2. We go to 5. We go to 6. We're done with 6. Where do we go back to? 5, and we're done with 5. We go back to 2, and we're done with 2. And it turns out that a valid topological ordering, so this list that we were building, this 741306552, we just flip that around. And we end up with a valid ordering in which we can do our tasks. Is there any questions before I talk about intuitively why this works? Yeah. So it's a good topological ordering in the sense that if we do task 2, then 5, then 6, that's fine, right? If we then do task 0, okay, that's another good one to do. We can do 3 next because we've satisfied both of our constraints. Then 1, then 4, then 7. Yeah. So it's valid. Yeah. What if you had a cycle? Okay. So that's an interesting question. Let's say I had a cycle, so I have an edge that goes back from 7 to 0. So how would we fix this? Or what can we observe about this? So this algorithm fails if you have a cycle. But it's also impossible to find a good ordering. So if you have to take 61A before 61B, and 61B before 61C, and 61C before 61A, you will not graduate. That's just how it goes. So it doesn't exist. There is no such thing as a topological sort if you have cycles. So then intuitively why this works is that as we're running DFS, the idea is that when we finish a DFS, that's, if we look at the ordering in which things got, actually you can see right here. 7 is the first vertex that finished. And just intuitively, it's a thing that should happen later. So just vague, and this is very vague, but if you do exam prep next week, well, you'll do a proof of this. But basically 7, because we finished early, you could think of these numbers that are at the front as the tasks that should be done later, because that's what DFS finished first. It's like the thing's deepest in the prerequisite chain, and so the natural thing you might do is reverse it. And it is not clear, and it should not be clear to you. Maybe it is, but it probably is not clear to most people that this is correct. And again, exam prep section will go through the details. Okay. All right. That's kind of a cute algorithm. Okay. Now, why is it called a topological sort? Well, it's because you can think of it as sorting the vertices. So the topological sort we came up with was 2, 5, 6, 0, 3, 1, 4, 7. So if I just take these vertices, I got ungroup. So if I take them and I drag them around, say like 2, no, okay, I got to ungroup again. But they aren't grouped. Okay, there we go. Okay, so here's 5. Okay, here's 6. Here's 0. It's going to look pretty ugly. Here's 3. Here's 1. Here's 4. And the where I'm getting this order is my topological sort down there. So I drag them all this way. And what you'll notice, if you look at the arrowheads carefully, what do you notice about them? They're all pointing in some rightward direction. So if you take this tangled web of chaos and you make it look nicer, this is the same graph. And so in this diagram, we have sorted our vertices so that they all point in the same direction, and we can manifestly see we have obeyed all of our constraints. All right, any questions about this? So graph algorithms, if you go into CS theory, it's very rich. There's all these problems that are basically run depth first search and do something along the way. In this case, it's write down the order in which you do the DFS post order. And in this case, we also restarted. One quick note I want to mention, too, about the term depth first search. I'm going to make a slide because I thought about this while talking. Depth first search. Be aware that when people say depth first search, they sometimes mean with restarts, and they sometimes mean without. So for example, when we did depth first paths for reachability, we did not restart. For topological sort, we restarted from every vertex with in degree 0. Okay? So just be aware that depth first search is a generic term that refers to both of those things. It's context sensitive. So if you ever ask a TA, does depth first search mean it restarts or not? The answer is undefined. You have to actually also say that. Yeah. That's a great question. Okay, so the question was, there's also, I'll make another slide for that one. Question. What is the runtime to find all vertices of in degree 0? Interesting thing I did not tell you. You don't have to. So another better topological sort algorithm is run DFS from an arbitrary vertex. If not all marked, pick an unmarked vertex and do it again. Repeat until done. So you don't have to start at the in degree 0, but I don't want to go there. Yeah. So I think it's intuitive that you should start at the in degree 0 vertices, but you can actually start it anywhere. And as long as you do restarts, it works. It's kind of a surprising fact. All right, yeah. Well, I could say run depth first search and then give the DFS post order of this graph, and if you hit a dead end, restart somewhere else. That would seem fine. But I would have to explain that. Yeah. All right. Great. So that's topological sorting. Okay. So what I'd like you to do is, given this graph, tell me what a good topological sort would be. You do not need to use that algorithm I just told you. But I want you to see if you can come up with one. And this will be important because we're going to solve another graph problem in a minute. And again, you do not have to do the post order thing. You can just use your eyeballs if you want. In fact, it's easier not to use the algorithm we just described. Okay, wherever you got, I'll give you an answer. 0, 3, 1, 2, 4, 5. And you can do the DFS post order if you want, but you can also just look at it. All right. Any questions about that? Okay. Why did we do that? Well, because we're going to talk about shortest path next in a minute. All right. Now, quick note, what someone mentioned earlier, what happens if you have a cycle? Just so it's also on a slide that's here permanently. This only works if you have no cycles. And in particular, I'm going to introduce a term here that's really important, which is directed acyclic graph. And that's any graph which is directed and has no cycles. It's a very special class of graph, and it turns out there are tons of algorithms out there that only work on DAGs, and this is one of them. Okay. All right. So we solved one graph problem. Let's do some more. So let's talk about shortest paths on directed acyclic graphs. So I'd like you just to, let your brain do something that's not listen to me again. Try and figure out what is the shortest paths tree for this graph, and extra bonus question, in what order does Dijkstra's algorithm visit the vertices? Just try and figure out what the shortest paths tree is. Just using S as the source. Okay, spoiling it. All right, so that's the shortest paths tree. Assuming I didn't mess it up. Looks good to me. Okay, so that's the best possible path to every vertex. And the order that Dijkstra's algorithm visits the vertices is 0, 1, 3, 4, 5, 2. Keep in mind, that's the same distance. Well, actually, if you had to describe Dijkstra's in a few words, you would say Dijkstra's visit the vertices in what order? Yeah, closest to the source. Okay, so that's how I know it's 0, 1, 3, 4, 5, 2. Okay. All right. Now, if we allow negative edges, it turns out Dijkstra's algorithm can fail. So, for example, this graph I've put together here, this is Dijkstra's algorithm running, and this is just before it visits vertex 2. Okay? So at this point, we have a good shortest paths tree. Once we visit vertex 2, we're going to relax these two edges. Is minus 20 plus 7 better than 2? Yes. Okay, so we're going to change that value to minus 13. And so this value will be correct. It gets updated to minus 13. This edge, though, is it better to go 7 plus 1 to 8? No, that's worse than 3. So we're going to accept this edge. We're going to relax it and say the relaxation succeeded. This one fails. And so ultimately, what ends up happening once the algorithm completes is that the distance to 5 is wrong. Okay? So Dijkstra's can fail. In this case, it gives the correct edges, but it gives the wrong distance to value. And the problem is that it doesn't revisit this edge here. It never reconsiders that. Okay? So Dijkstra's with negative edges can fail. How do you fix it? Well, you can actually just revisit everything again. And I mentioned just out loud once, there exists a shortest paths algorithm, which is literally just relax all of the edges v times. And that's called Bellman-Ford. It's the simplest algorithm around. And it's guaranteed to work. It's slower. But I'm going to show you a different way. Okay? So you could say one way to fix this is let's just revisit some of the vertices, but I'm going to do it a better way. Okay? All right, so everybody see what the problem is? Got a negative edge, we got the wrong value. Okay. So what I'd like you to do now is try to come up with an algorithm for shortest paths specifically on a DAG. That is a directed graph with no cycles. You should still use the idea of relaxing edges. That should be a good building block in your mind for how to solve it. And it's supposed to work even if there's negative edges. So I'll give you guys a minute or so to think about how you might do that. This is an easier problem than topological sort. Okay, what do you think? What can you do? So Dijkstra's, you visit your vertices in the order of their distance from the source. What can you do here? Any ideas? So it's a directed acyclic graph. Magnitude. Nope, don't like that. Value. Nope, don't like it. I'll give you guys a hint. Yeah. Visit them in topological order. So the basic idea is you just go through all the vertices in topological order, and when you visit, you relax all of its outgoing edges. And this will work because every vertex, you're only going to visit it once you've considered all possible information about it. You've handled everything upstream of yourself. Okay, let's see if I have a demo here. Yeah. So basically, the algorithm would look like this. Given a graph, first find a topological order. You guys did that. Okay. Turns out that's V plus E to do all those depth first searches. Next, we just relax all the edges. This will look pretty much like Dijkstra's, but this is just to prove to you that this works. Okay, so let's try it out. So this is like Dijkstra's. It's just that we're going to relax the edges. Instead of having a fringe, which is ordered based on distance from the source, we have a fringe which is just the topological order. Otherwise, it's exactly the same. So we start at 0. Okay, is 1 better than infinity? Yep, so is that. Those are both better. Okay, which vertex comes next? 3. Why? Because that's the next in the topological order. Okay? Which of these two, is 2 better than 1? No. Is 2 better than infinity? Yes. Okay? Now at this point, actually, I'm going to wait before I say why it works. Next vertex to come off is what? 1. We're just going in order. All right. So what's this value going to be? 7. Okay, good. All right. Now we consider the negative edge. Now, what's special about this compared to Dijkstra's is we're going in the order of kind of the order of the dependencies. So at this point, there's nothing earlier that could possibly, we've processed all possible upstream information of vertex 2. So we don't have to worry about any negative weird stuff happening. We're going in a direction, we're following the flow of possible information. So what's this going to become? negative 13. Okay? Next comes 4. All right, negative 13 and 1 is negative 12. So any questions about this algorithm? So it's cute. It exploits the fact that with the topological ordering, you don't need to think about what's upstream. Or sorry, what's downstream. Okay? All right. So that's pretty cute. Okay. So this runtime is V plus E. And a quick note, in office hours yesterday, someone asked me, if you're going to V vertices and relaxing all of the edges each time, shouldn't it be V times E? Because there's V vertices and E edges, and we're doing all of the edges every time there's a vertex. And the reason that is not the case is a reminder that when we say E, we mean the total number of edges. So here there are 8 edges. If you think of E as the average number of edges, I guess it would be V times E overall. But I don't want to go there. All right. Just a reminder, E is all the edges. Okay? So that's pretty cute. All right, let's do something weirder. So hopefully you found that not too intimidating. We're just going to keep going. Any questions about this before we continue? Yeah. This is called the DAG shortest path tree algorithm. It doesn't have a cool name. So that's the directed acyclic graph shortest path tree algorithm. Yeah. All right. Let's talk about longest paths. Okay. So consider the problem of finding the longest paths tree from S to every other vertex. Now, one rule I'm going to say is we're not going to allow cycles. Otherwise, it's cheating because we could just go in circles. Like we could go 0, 1, 4, 6, 3, 4, 6, 3, 4, 6, 3, 4, 6, 3 forever. That's the lame problem. So we're going to restrict ourselves to simple paths, no cycles. And so, for example, on this tree, that is the longest. On this graph, the longest paths tree is as shown. Okay, I'm going to tell you 2 facts that might surprise you. One, there is no good algorithm to do this. Nobody knows of one. The best known algorithm is exponential time, which is very bad. That means if you have a graph of 40 vertices, you can't find the longest paths tree, unless it has special properties. But if you generate a random graph of 40 vertices, you're never going to find, unless you spend, say 100 vertices. Not going to happen. That's too big. Second, this is probably the most important unsolved problem in math. Now that seems weird. You think you would have heard about this. You have, but I won't tell you. There's another name for this. Actually, anybody know? It's like the traveling salesman problem. Yeah. In fact, this problem, it turns out, is equivalent to a ton of other unsolved problems in math. That's why it's so important. But I'll save that for the last week of class. So I think that's interesting, that shortest paths, we just knocked it out in one day. No problem. Pretty fast algorithm. But longest paths, that's very hard. No human has found it. The best known algorithm that a computer can run is exponential, and it's very important. So I'd like you to solve it on DAGs. Okay? Now, if you solve it on general graphs, you'll be the most famous person of our generation, perhaps. But I'm going to have you guys try and just solve it on DAGs. Okay? I'm going to give you guys a solid minute and a half to think about this. And I'll give you a hint. You can use some of the tools from today. Okay, I believe in you. All right, does anybody see the trick? I'm going to try and get someone I don't usually hear from if possible. Sorry. Okay, go ahead. Yeah. 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 Yep. Make the edges negative. Run the DAG shortest paths tree. Flip them back. That's it. So given a graph, you form a new copy with the edges flipped. You run DAG shortest paths tree on G prime, our new graph. Then you just flip all the distance 2 values and you're good. Okay? That's it. That's very cool. I think that's a really beautiful algorithm. All right. Now I want to make a quick note here. If you're somebody that has mathematical maturity, this phrase that gets thrown around in the department and in the world, I will say that this algorithm should just seem plainly correct. For those of you who are, like on the more mathematically mature end of things, there's almost nothing to say. It's like, well, we know that the DAG shortest paths tree works on graphs with negative edge weights. We know that. And we also know that if we negate the sum of a bunch of negatives, then we get some positives. And there's really not a lot of meat to it. I mean, it feels like almost cheating. So you get scared. You're like, maybe there's some catch I'm missing. But the more mathematically mature you are, the more that you trust that this actually works. Now, one of the things I should mention is that this mathematical maturity, actually I'm going to click on this link. I didn't know there's a Wikipedia article about this until yesterday. It's really nice. So it's an informal term used by mathematicians to refer to a mixture of mathematical experience and insight that cannot be directly taught. Instead, it comes from repeated exposure to mathematical concepts. And it allows you to do, for example, it gives you the capacity to handle increasingly abstract ideas. So if you are somebody who is, math Olympiad, whatever else, yada, yada, yada background, then perhaps this just seems like, okay, I know this thing. It feels like things I've seen before. And for those of you who came in with less math background, these problems are a little scarier. Now, luckily for you in 61B, this hasn't been a major focus of really pushing mathematical maturity. We've been focusing more on independence as a programmer. But if you go on to 16A, 16B, 70, 170, they're a little more focused on this. Okay? So I just want to throw that out there. That thing, the sort of ephemeral, like what is that some people can do that I can't quite do, or whatever that I'm learning how to do? Where does it come from? Well, it's this repeated exposure. Just throwing that out there. I'll have more thoughts on this in a bit. Okay. All right. Exercise for later. I think you might enjoy. Now, why is it doesn't seem like longest path should be hard on general graphs. So what I'd like you to do is try and solve it on this graph. Not now, but later. Just try and get an intuition for why longest paths is hard. It's a little subtle. And if you can't quite get it into your brain, then try Googling why longest path's hard. I think it's kind of a fun exercise, though you're working on midterm studying, so don't do it yet. All right. So some graph problems. We've got topological sort. We have our DAG shortest paths algorithm. We talked about longest paths, and we don't have a good runtime for this. And DAG longest paths, we can kind of cheat. Okay. This brings me to my last official topic of the day, which is reductions. So this is a preview of what you'll see if you take 170. And it's a really nice idea. Okay. So the problem solving that we just did, it probably felt a little different than what you've done in the past. We basically took a problem, in this case a graph, and we pre-processed it. We turned it into the negative of itself. We then fed it to a different algorithm, DAG shortest paths, that produced a shortest paths tree for G prime, and then we post-processed it by flipping all the signs. Okay? Now this entire box, which had a pre-processing step, using some other algorithm, and post-processing, together it formed a new algorithm, which was DAG longest paths tree. Okay? Now this is an incredibly important idea in computer science theory, but it's something you do informally all over the place. If you take AI classes, it's a similar kind of thing, where I have a black box that I throw data at, and now it knows how to play Pac-Man or whatever, right? That's as you'll do someday when you do 188, if you do it. Okay, and so this idea is known as a reduction. Okay, so this process is known as reduction in CS theory. So since, and this is the way that I never liked the term, but I'm just going to go with it. So since DAG shortest paths tree could be used to solve, that was a late night. So since DAG shortest paths tree is a building block that could be used to solve DAG longest paths tree, the way that people talk about this is they say that longest paths tree reduces to shortest paths tree. It basically just boils down to shortest paths tree. Now, I think the direction of the transitivity of the verb is backwards from what it should be, but that's how they do it. Okay. Now, as a real-world analog to this, imagine you want to climb a hill. There's lots of different ways to climb a hill. Like you can fly an airplane to the top of the hill. You can get shot out of a catapult or a cannon or whatever. You can ride a horse to the top. And so you could say, just so, climbing a hill, it just reduces to riding a ski lift. These are ways to solve it. Okay? So that's what reduction is informally. Okay? Now, we can give a more precise definition. The algorithms textbook used in 170, they define reduction without going into too much math. As if a subroutine for task Q can be used to solve P, we say P reduces to Q. Now, I would have used something like, I will later use a verb that goes in the other direction and say, No, I'm not going to go there. Why not? I'll save it for later. All right. We can also define this idea formally, like what does it mean to use a subroutine to solve a task? You can read about Karp and Cook reductions. This is if you want to go really deep into CS theory land. It's not that bad, but it's far beyond anything I want to talk about. Okay. So there is a formal notion that has to do with Turing machines and da-da-da-da-da, and you can put this down really firm mathematical footing, but all you need to know is this diagram, basically. I want you to understand that this is a possibility for solving problems. Now, I want to give you, before we go, a richer example of reduction than just flipping some signs, because that's not so truly satisfying. So I'm going to give you just a couple of new problems you've never heard of, perhaps. This is called the independent set problem. And given a graph, an independent set is a set of vertices where in which no two of the vertices are adjacent. So in other words, I color some of my vertices white, some of them red, and none of the red vertices touch. Okay? So the independent set problem on this graph says, does there exist an independent set of size k? Can I find 9 vertices that I can color red so that none of those red vertices are touching? And so for here, this example, we have n equals 24. There are 24 vertices. In this specific crazy cool shape, if you run the independent set solver that might exist out there, this is one particular answer you might get. So you'll see that no 2 red vertices touch. Okay? So do you understand what independent set is? Okay. Now I'm going to tell you about another problem called 3-SAT, another really important one. And today is a smorgasbord. I'm just trying to I'm not, on the midterm, I'm not going to be like, well, this isn't in scope for the midterm. But on the final, I'm not just going to assume that you know what independent set is and 3-SAT and all this. I'm just trying to give a survey of problems out there in the world. That's why we're whipping through so many. Okay? So 3-SAT is another problem which says, hey, I'm given a Boolean formula. So does there exist a truth value that you can assign to each of the Booleans so that everything ends up being true? And 3-SAT refers to the fact that that the equation is always going to be 3 variable OR statements. So x1 or x2 or not x3. And I'm going to AND a bunch of those. These are known as disjunctive constraints. So for example, if I say x1 is true, what will x1 or x2 or not x3 be? It'll be true. So that one's true because of x1. This one's true also because of x1. This one's true because x2 is true. So there's many possible ways to satisfy this equation. Okay. Why am I telling you about these problems? Well, it turns out that 3-SAT reduces the independent set. That is, given a 3-SAT problem you might want to solve, you can build a graph and ask if there exists an independent set and solve it. This is a very deep, this was a major paper at the time it was discovered, along with some other reductions like this. So this is really deep, crazy stuff to throw at you all at once. But I'll give you an example of how it works, just to give you a flavor, right? Again, I'm not expecting you to fully digest this, and this is something you would go on to learn in 170 or 270. But this is how you can show that 3-SAT reduces the independent set. So for every one of these 3 variable clauses, you form yourself a little triad of vertices. 3 vertices in a triangle, all touching. And you give them a name, corresponding to whether or not it's a variable or a variable's negation. Then you will add an edge between, so you add edges between those 3. And then you'll add an edge between every variable and its negation. So x1 is going to have an edge to not x1, and x1 is going to have an edge to the other not x1. And this, it turns out, will allow you to solve 3-SAT if you can find an independent set. Now, I've just gone through, again, we could have done an entire lecture on this. But this is a reduction. So I'd like to see if it helps sink into your brain a little bit. Okay, so even if you didn't understand all those details, trust me that given this equation, this is the appropriate graph. So what I'd like you to do now is find me an independent set, and then try and figure out how to post-process it to give you a set of variables you can assign. So give it a shot. I know we're going into really deep territory today, but hey. So find me an independent set. In other words, color 4 of the vertices red so that they do not touch. And then try and figure out a solution to the 3-SAT problem out of that. Someone give me an independent set. Pick one of these for me. X3, great. Okay, let's color it red. Okay, give me another one. I want something out of here. X2. Now you notice I need to pick one in each. I can't pick. I can't never pick X4 or not X1, right? Because I already picked something from the triangle. How about here? X3. That seems good to me. Okay, and one more. X4. Okay. Well, I'll do X4. Sure. All right. So now I have found an independent set. And so what do I do with that? How does that help me solve 3-sat? Well, this tells me that I should assign X3 what? True. X2, what should I assign it? False. X4? True. X1? Doesn't matter. Okay? You can pick whichever one you want. So I've come up with 2 possible solutions here. Okay? Now this is pretty deep. Okay? Again, I'm not expecting you to walk out of this room being like, of course, surely, it is so, Socrates. But it's a rich thing pointing out that here, if we look at the reduction graph, because independent set, if you had a solver for it, can solve 3-sat, we could do the following. So given, why does it look so weird? Who did this? What? It looks, I see. Aha. Okay, I gotta make this wider. When one of you guys works at Google Slides, I need you to fix this for me. All right, thank you. All right, so if I wanted to solve a 3-sat problem, I can pre-process it into a graph, run it through an independent set solver. Unfortunately, that's exponential time, but whatever. Get me back an independent set, post-process it. There you go. Okay. So reductions are a really, really powerful idea. All right. Now, arguably, we've been doing something kind of like reduction throughout the course. You could think about abstract lists, they just reduce to arrays in some sense, or percolation just reduces to disjoint sets. Now, those aren't reductions exactly, because it's not that we're just calling some simple little subroutine. So I think a better term for this would be decomposition, which is taking a complicated problem and breaking it down into little parts. And I would say that's really the heart of computer science. That's what matters. And I know that we've gone through a lot of really intimidating problems here, but I hope that you enjoyed being along for the ride and seeing what you could learn. And I would say, crucially, knowing the appropriate abstractions makes solving problems way easier. So I'm gonna close because I want to tell you about this guy. So James Flynn, who's heard of the Flynn effect? Okay, I'm gonna tell you about it. He's gonna tell you about it. So, okay. Here we go. I'm gonna 1.25 this. Sounds bad. I don't know. Oh, that's not good. Why does he sound terrible? Oh well, okay. Let's try. I'm gonna do it. If not, I'm just gonna have you watch it later. He sounds like a darn robot. Reading humans. Okay. Well, I'm gonna summarize that. Okay. I'm gonna do my version. So, this is hard because he spent all this time practicing. So basically, the theory. I'll let him talk behind me. Okay. So he basically says, generationally, he's a guy who studied human intelligence over his life. And he's noted that people have gotten smarter, it seems. So if you look at IQ tests from way back at the dawn of IQ tests, if you score them based on modern IQ tests, they would only have an IQ of 70, which is pretty bad. And if you take our modern people and have them do the old scoring, we would have an IQ of 130. So the question is, are we way smarter than our ancestors? Is human evolution doing something crazy where people are just vastly more intelligent than in the past? And the answer, he says, he was curious why this is. And so he says, really, the reason he thinks that there's a difference now is because of the much more powerful abstraction machinery that we have available to us today. And he gives an example, which is that if you were to study how many bullets are in a target at a shooting range, and you tried to compare what it looked like in 1850 versus 1950 or something, you would see a dramatic change. And it's not because of the fact that people are better at firing guns, but because guns themselves change. And he argues that the abstractions we built up in modern industrial society are very similar. And in particular, he cites the ability to engage, for example, hypotheticals and abstractly reason about things is the key reason why we can just decimate our ancestors at these abstract reasoning problems. And that's part of what we're trying to get you guys to be able to do. This talk is very good, so I encourage you to check it out later. So be aware, the tools that we're giving you are pretty good. Now, there is no time, so I will not answer any questions, but if you want to ask anything, I'll be at the front of the room. So I hope you enjoyed the wild ride to Reduction Town, and we'll be back on our normal, not so crazy trajectory on Monday. Thank you.